Hello everyone. In this video, we're going to look at how we graphically represent sensitivity analysis when we're dealing with the objective function. If we recall from previous units that what we're doing with sensitivity analysis is seeing how much we can alter something within our model and track how that affects other aspects of our model. So in this case, when we're talking about performing sensitivity analysis on the objective function, what we're going to see is how much we can alter a certain aspect of that objective function and still continue to have the same optimal decision. There will be certain aspects of things that I'm doing here that I will not cover because we've already covered them in the past. So we have already learned how to graph the constraints of our linear program, which I've already done in this question. I have already also identified the feasible area. And really, this is just the model that we've been working with all through our previous unit, dealing with the farmer who has a certain amount of acres of wheat that he's trying to decide to plant and a certain amount of acres of barley that he's trying to decide to plant. So this is the exact same graph, the same model that we've been dealing with, and I'll be bringing back those constraint formulas in a minute. Another thing that we already found was how to graph the objective function onto this, which I will do now. So here now with our objective function on our graph, we would now slide this in keeping that slope the exact same and finding the point at which it was just about to leave the feasible region, which was right about here. And because of that, we chose this point here, the intersection of the acreage constraint and the pesticide constraint, to be where our optimal solution occurred. Well, what we're doing now is we're saying, what if this wasn't the line that represented my objective function? How much could I alter certain aspects of that line and maintain having that exact same point as my optimal solution point? So if I was to imagine if that line did not have quite so aggressive a negative slope, if the slope of this line was something more like this, well, as I graph that, I would get it on my graph, and then I would slide that again, and I see that, oh, that no longer leaves the area where the optimal solution used to be, but that would cause my optimal solution to now occur at the intersection point of the acreage constraint and the y-axis. Similarly, if that slope was even more aggressive, if the slope was something more like this, again, after we graph that function and we slid that line sideways, what we would find is that this would now be our optimal solution point, the point at which our pesticide constraint intersects with the x-axis. What our goal is here is to find out mathematically how much can I adjust the slope of this objective function line. How much can I tweak that slope and still maintain to have my optimal solution where it initially was at the intersection of the acreage and the pesticide constraint? What we are going to need in order to see how much that slope of the objective function can be altered is three things. One, we will need the slope of the objective function. And then second and third, we will need the slope of the two binding constraints. With those three things and a little bit of math, we will be able to perform sensitivity analysis on the objective function. So let's begin by dealing with the slope of the two binding constraints. Beginning with the slope of our acreage constraint, and if we remember back to our previous work, our acreage constraint was originally written W plus B has to be less than or equal to 8. And we remember as we are writing these and working things around, we disregard the inequality and we just set that to equals to 8. One thing that is absolutely key to pay attention to is how we listed our axes. Paying attention to the fact that we put barley on the y-axis and wheat on the x-axis. If we remember back to the basic equation of a line, which is y equals mx plus b, where B represents the y-intercept and M represents the slope. Here, what we're concerned with is the slope. But why it is important to pay attention to how we label the axis is because we need to make sure that this value of y is over here by itself. So in this case, our y-axis, which is symbolized by our Barley constraint, we want to rearrange this formula, isolating for b, or Barley, on the left-hand side of the constraint, and we would simply be left with the equation y equals 8 minus w. And remember, back to our equation of the line, y equals mx plus b. It is the item with x that signifies what our slope is. Well, with x here, what we have is an unwritten 1. So therefore, the slope of the acreage line is minus 1. So getting rid of this, we have now that the slope here is equal to minus 1. That is the slope of our acreage constraint. Similarly, with pesticide, we are now going to find the slope of our pesticide constraint. Well, initially, pesticide was written as 2w plus b is less than or equal to 10. Again, disregarding the inequality, just setting that to equals to, and once again wanting to get it into the form of y equals mx plus b. So isolating for b on the side all by itself, once again, because Barley is our y-axis variable. So rearranging this, we end up with b is equal to 10 minus 2w. We have a slope of minus 2. So the slope of this line is minus 2. Now what we should find, and the reason why that this point ended up being our optimal solution point, is because the slope of our objective function is somewhere between minus 1 and minus 2, and that is what ended up having us to decide, as we did this graphically before, even without us knowing this, is the reason why we ended up choosing our optimal solution point as the intersection of these two lines. So hopefully, as we go and solve for the slope of our objective function, we will find that it is somewhere between minus 1 and minus 2. Initially, our objective function was listed as 5,000 w plus 3,000 b, and that is it. Again, that is not the equation of a line. To get the equation of a line, I need to have that set to something. I'll tell you, it really doesn't matter what you have that set to, what you make that equal to. Anything is fine. Previously, to graph it easily, we chose a value of 15,000, but you can choose anything you want. It really will not affect anything. Whatever value you choose here will have zero impact on what the slope will be for this line. The only impact it will have is on what the y-intercept would be. So even if I chose, say, a slope of 1,000 here, or 1 or anything, I'm going to end up with the same slope. So again, doing a little algebra, 3,000 b would be equal to 1,000 minus 5,000 w. And now dividing the 3,000 to the other side, we would end up with, I could do the entire side, which I'll do at first this time. We would end up with the entire side divided by 3,000. Mathematically, how I've listed this now would be the exact same as if I separate those two terms and said that this was 1,000 over 3,000, or 1/3, minus 5,000 over 3,000 w. The coefficient with our x variable term, our x-axis variable, which in this case is w, the coefficient of that is the slope of our line. Or in this case, the slope of the line would be minus 5,000 over 3,000, which in terms of simplifying this, I could simply write that that was a slope of minus 5/3, which, as we said, should occur somewhere between the slope of minus 1 and minus 2, And if I was to change that to decimal form, that is a slope of approximately minus 1.67, which is exactly where we said it should be, somewhere between the slope of minus 1 and minus 2. And again, that was the reason that that point, this point here, ended up being our optimal solution point. The only thing that we found at this point is the slope of the three lines. What we want to do now is to look back to our initial objective function, again, which I've written here. I'll get all the rest of this out of the way. Our initial objective function, we want to see how much are we able to adjust this coefficient of W and still maintain having our optimal solution be that same point. How much can we adjust the coefficient of B and have our optimal solution remain at that same point? Getting back to one of the key aspects of sensitivity analysis, we can only adjust one of those things at a time. So first, let's deal with the coefficient of W. What would happen if the price of wheat went up or went down? At what point will we change our optimal decision? If we remember back to what our optimal decision was, and it really doesn't matter for this, but our optimal decision, again, remember, represented by this point, was to plant 2 acres of wheat and 6 acres of barley. But as the price of these two different crops change, so may our decision of how much to plant. At what point will I choose to plant more barley or less barley or more wheat or less wheat? That's what we're looking to find here. Let's begin by exploring with the coefficient of W. So again, let me get some of this stuff out of the way here. Okay, so I just adjusted the slope of our objective function line to sort of be in the same scale as our other two slopes, and to show that it did sit somewhere between -1 and -2. What I would suggest as you do this is, as you work through the equation, do not simplify the slope of that line. Keep it in the same units that it was originally in. And hopefully you'll see why I'm going to do that in 1 second here. So I'm going to just switch that back to be, once again, that this slope was, keeping it in its original units, was 5,000 over 3,000. Now, the reason why I am going to do this is because if I did the conversion, what I'm going to have to do in the end is to convert it back to be in the same units that it was originally in, thousands of dollars. If I keep it without doing the adjustment, I won't have to do a secondary conversion with it. Because what I'm going to do now for each part of this fraction, first starting with the 5,000, which represents the coefficient of wheat, I'm going to compare it to the slope of the one constraint, and then I'm going to compare it to the slope of the other constraint. I will need to do that for both the numerator and the denominator of this slope. So first, dealing with the 5,000, which represents the coefficient of wheat, if I say that the slope right now of my objective function is minus 5,000 over 3,000, this point here will remain my optimal solution as long as this line here, my objective function line slope, does not all of a sudden go higher than whatever this acreage constraint was, or in this case, -1. So if that was exactly a slope of -1, I would be left with the special case of alternative optimal solutions. So I would be able to choose anywhere on this line between these 2 points, and any of that would be an optimal solution point. But as soon as the slope of this line, of my objective function line, goes above -1, once that slope goes above -1, all of a sudden my optimal solution point will no longer be where it was. It will now be this point here. So what I'm going to do is set this to be equal to -1, and again, -1 because that is the slope of this line. I said I was first going to do this with wheat, and I'm going to set whatever variable was associated with wheat, which is the 5,000, I'm going to set that to be an unknown. okay, or in this case, x. So if I arrange this function now, what it is telling me, so as I simply multiply the minus 3,000 to the other side, is that x was originally 5,000. The price of wheat was originally 5,000. That price of wheat could drop down to $3,000. I would still continue to plant 2 acres of wheat and 6 acres of barley. But once the price of wheat drops below $3,000, my optimal solution would change, and it would change to the point where I'm now going to plant 8 acres of barley and no wheat at all. I would do that exact same calculation, but now setting that to be my equal to the second slope. So if I did now x over 3,000, again, I'm altering the variable associated with wheat. One at a time would now be equal to the slope of minus 2. Again, doing the math to isolate for x. We would now end up with x could grow, the price of barley could grow to $6,000, and my optimal solution would continue to be the same. Once again, what we'd be seeing is this slope here, once it crosses, until it gets to that minus 2, again, exactly at a slope of minus 2, we would have alternate optimal solutions, in which case I could pick anywhere on this line now. Any point there would give me the same profit. Once it goes beyond a slope of minus 2, now my optimal solution point will change again, and I would pick here. I would pick to plant only wheat and no barley. I would be planting 5 acres of wheat and no barley. But until that point, my optimal solution point would remain planting 2 acres of wheat, 6 acres of barley. The optimal solution remains the same. Another thing to pay really close attention to here is notice that not only did we say that the slope of that objective function should be somewhere between the slopes of the two binding constraints. Notice now that as we altered the coefficient of 5,000, as I altered it and compared it to the one slope, in the first slope of minus 1, the price of wheat was dropped down to $3,000. As I compared it to the other slope, the price of wheat increased. And that will always be the case. What you should find is as I compare it to one of each of these slopes, in one case it's going to decrease, in the other case it's going to increase. And what I would say now, performing sensitivity analysis on this first coefficient, so as we've seen that wheat can alter anywhere between $3,000 and $6,000 in price, and I would continue to have the same optimal decision. What we call that is the range of optimality. So the range of optimality for wheat would be between $3,000 and $6,000. As long as wheat, and remember I can only change one thing at a time here, as long as the price doesn't drop below $3,000 or go above $6,000, I will still continue to plant 2 acres of wheat and 6 acres of barley. It is really important to take note here that when I'm talking about the range of optimality, within that range, my optimal solution will not change, planting 2 acres of wheat and 6 acres of barley, but definitely the maximum profit will change. As soon as I alter either of these two coefficients, as soon as the price of wheat changes or the price of barley changes, it will definitely change my maximum profit. But what it will not affect, unless it goes beyond the range of optimality, what it will not affect is how many acres of each, or what my optimal solution is. So quickly, let's go and find the range of optimality for barley. Again, we're going to have to do this twice. Once, we will be altering now the coefficient for barley and comparing it to the slope of minus 1. And then we will do it again, comparing it to the slope of minus 2 for my other binding constraint. So initially setting this 5,000 over 3,000 equal to -1. But again, now we will be altering the $3,000 coefficient, the coefficient of barley. Quickest way I think to do it is just to sort of alter these two variables. So I would end up with -5,000 over -1 is equal to x, or x is equal to 5,000. So right now, the price of barley is $3,000 per acre. That could go up to $5,000 per acre, and I wouldn't change my decision. And now notice, because here, our value for barley went up, as I compare my objective function slope to the other constraint, the price should go down. And if that doesn't happen, I know I've done something wrong. So I will start with that same -5,000 over 3,000, or in this case, x. What we're going to alter should be equal to -2. And again, just reversing these two, we would end up with -5,000 over -2 is equal to x, or x is equal to 2,500, which it did go down from its initial value of 3,000. It went down to 2,500. In one instance, it went up. In the other instance, it went down. We're feeling pretty confident that everything has gone okay. And once again, we could express now our range of optimality for barley to be between $2,500 and $5,000 would be our range of optimality for barley. Once again, critical to remember, only one of those two can be altered at a time. I can only alter the coefficient for wheat or the coefficient for barley. If both of those change, then I automatically would have to reformulate the entire model. Okay, but as long as only one of those changes, if barley went up to $4,000, I don't need to worry about reformulating this. I know that because barley has not gone above $5,000 an acre, I would not change my optimal solution. I would still continue to plant 6 acres of barley and 2 acres of wheat. So please stay tuned for the next video, where I'm going to show you how to really quickly double check what we just calculated with the use of Excel. Thank you very much, everyone. Please make sure you practice as much as possible with this, and email me with any questions that you may have.